Thank you. So let me just remind people of where we were last night, in case you also drank a lot of wine and forgot everything. So, so we have a probability distribution P, which we think of as a convex combination of probability distributions PU, and we want to look at the hypothesis testing task, which is whether an observation comes from P or it comes from Q. And we had this likelihood ratio Lu of y is Pu of y divided by Q of y, and L of y is P of y divided by Q of y. So, and we define this inner product, right? Fg is the expectation of y from Q, f of y, g of y. And then we showed, or I left it as an exercise, that if the norm of this likelihood ratio, if it's 1 plus little of 1, then there is no even weak distinguisher. And if it's O of 1, there is at least no strong distinguisher. So let's just say, in general, this norm is small. The task is hard, but not hard, impossible in some sense. You cannot do a very good job at distinguishing between these two probability distribution. And this is the norm of the norm of this likelihood ratio. It's also known as the chi-square divergence. So chi-square divergence is defined, one way to define it is, the norm minus 1. And, or we can write it as expectation over y from P, the ratio of Py over Qy minus 1. And someone asked me a very nice question, which was, why do we use chi-square divergence and why don't we use KL divergence? So what's the difference between the chi-square divergence and the KL divergence? So the KL divergence of PQ is the expectation of y of log of P of y over Q of y. And so roughly speaking, if we only care about if we only care about the kind of the case where we only care about distinguishing whether this goes to infinity, whether these quantities kind of are small or go to infinity, then this is basically the same, or up to that, as a log of the expectation of P of y, Q of y, right? So if that log, we only care about the question of whether this quantity kind of goes to 0 or goes to infinity, then basically this we can put a log around here. So basically the difference between chi-squared and KL corresponds to basically whether you put the log in this side of the expectation or on that side of the expectation. Or, in physics speak, that would be the difference between a quenched quantity and an annealed quantity. And that difference can be sometimes very substantial. So let me remind you of this example. So we said suppose this example that basically the only difference between P and Q is that there is some Y star such that P of Y star is, I don't know, 2 to the minus 0.1 n, and but Q of Y star is 2 to the minus n. So in this case, if we look at the chi-squared difference, then the ratio is 2 to the right. The ratio between the likelihood ratio is 2 to the 0.9 n, and if you square that, that is 2 to the 1.8 n. That's so big that even though it happens in P with exponentially small probability, it still contributes an exponentially large quantity. So the chi-square divergence is going to be exponentially large. However, if you take log of this ratio, it's only polynomial, and you multiply a polynomial by the probability is inverse exponential. So the contribution to the KL divergence will be negligible. So in some sense, KL divergence captures better the difference, but the chi-squared is easier to compute. And if the chi-squared is low, then you know that it is hard. If so that would be good enough. And sometimes, especially in the cases we are interested in, that would be these kind of annealed quantities would be somehow good enough for us. And again, I think part of it is because, at least for some problems, we'll have this situation where basically we have some quantity that looks like, say, alpha n, and then say some quantity that looks like say n to the 1.5 or something like that, where basically this would be the statistical threshold, and this will be the computational threshold. So when you're in the statistical threshold, you really care about this constant in front of the alpha, and then you need to do all of these, to get these things right, you need to kind of look at these quenched quantities and do complex calculations, etc. But if you're anyway all the way up here, and also this computational threshold, again, like it's sometimes the constant even is not even really well defined, because it really would depend somehow on the running time. If your running time is polynomial, quasi-polynomial, and what exponent. So you really don't care so much about the particular constant. You want to really get the right power dependence. And then the difference between annealed and quenched becomes less substantial. It's like, if you're calculating say the US debt, deficit, then you probably don't need to worry about, the cents and dollar, right? To calculate it down to the last digit. And
what's the difference between weak and strong here?
So weak will be, so if we say define the sum of the errors, so let's say E1 is type 1 errors and E2 is type 2 errors. So weak means that this is less than 1 minus epsilon, and strong means that this goes to 0. So weak means this is bounded away from 1, then at least you get, or another way to think about it, if you think of the experiment where you, with probability half, you get a sample from P, with probability half, you get a sample for Q, then weak means you get some advantage, probability of success has a little bit better than a coin toss, it's some constant advantage over half, and strong means probability of success goes to 1. And again, like eventually, I know Nati complained, but eventually all of the things we'll talk will be some parameter of the problem size n. So there will be some meaning to O of 1 and little O of 1. And some meaning will be revealed at some point, some quantity you can relate. So, so what we showed in the last thing we showed was this spiked matrix model. Where we had lambda VV transpose plus Z. V should have been a unit vector, by the way. I said standard normally. No, it should be a unit vector, say a random unit vector. And in that model, we had a very nice characterization. Lambda is square root n over 2. And basically, in that model, in this regime, this is impossible. And when it's above, then it's easy. Oh, there isn't really a limit. You can go all the way. And when it's above, this is easy. And also the likelihood ratio kind of said, so when it's above, then in this regime, the norm goes to infinity, and here it was bounded. Okay. So that's so that was what we saw last time. So now I want to talk about the spiked tensor model. Say K tensor model. So it's basically the same thing, just I'm going to go to a higher order. So just look at lambda V tensor K plus Z. This time, again, V is, say, a random unit vector. And Z is now a normal of the right size n to the K. Okay, so so now we can do the same calculation as we did before. So so if we follow the same calculation, we'll see that the dot product of LU and LV is going to be e to the power of lambda to the K UV squared. UV to the K, sorry. No, the opposite thing. That makes no sense. Right. So if you do the exact same calculation, what we'll show is, or maybe I'll write it this way. Right. So if you do the exact same calculation, that so we will see that the dot product of LU and LV is e to the power lambda squared. Maybe there is a half there. I'm not going to worry about those things. Like I said, we're going to move beyond the case where constants matter. So there's also probably there's some constant here. There might be some constant here, but we are going to just care really about the power of n in the lambdas. So so this is basically the same calculation as we did last time. There it was, the dot product of UU transpose, VV transpose. Here it's U tensor to the K, V tensor to the K, but the coefficient is lambda, you get just lambda squared. Okay, so you get lambda squared. U tensor to the K or V tensor to the K, which we can also write as just UV to the power K. So now we want to look at the the norm squared of this, which is the expectation over U and V of LU LV. So dot product of random unit vectors. It's basically, right, so UV basically behaves like n0, 1 over n, except it cannot go to be larger than 1 if it's random unit vectors. So, so basically this will become, the dot product of E of lambda squared x to the k minus, so E between 0 to 1 minus nx squared dx. Right, let's see that I didn't mess up this. Yeah, that's good. Yes. So then we just want to say when this is this infinity and when this is this bounded. Right. So if so here basically we just look at the largest thing where lambda where x is 1. So so it's basically just we just ask the question: if lambda squared is much larger than n, then this will be this will go to infinity. If lambda squared is smaller than n, this will be bounded, or of n. Okay, so actually we get the same right. So we get the same type of so for the spike tensor. Yes. Let's say it's even to make things nice. But yeah, in general, these things like everything that we do for even k will also work for odd k with the same things. So right now it seems like there isn't really a difference. So it actually the same thing, lambda, which is roughly square root n. Then it is impossible up to here. Now it's also possible, right? So we said likelihood ratio doesn't the likelihood ratio doesn't necessarily tell you that once it's unbounded that you can actually you can distinguish. But if you don't care about efficient algorithms, then you can actually do it. So the only question is whether you can do it with the place we have on the board. So okay, let's use it. Right. So maybe I'll just extend the board just a little bit because so we'll dedicate this to the spike tensor problem. So up to so when lambda is smaller than square root n, this is impossible. When lambda is larger than square root n, then some constant times square root n, then this is possible. And the reason is the following: if you look at the say maximum over all unit vectors u of z u tensor k, then that would be roughly that would be roughly square root n. And the reason is the following: that this is basically so the way to think about it is the following: for every fixed vector u, this unit vector u, this is standard normal, because z is a standard normal vector, u is a unit vector, u tensor k is also a unit vector. So this is a standard normal vector. So this random variable, let's call it, I don't know, x, is distributed like a standard normal. So the probability that x is x is larger than say square root n is, or say 100 square root n is like e to the minus 100 or 100 squared n. So it's exponentially small. So now you can do some kind of an epsilon net type of argument. You can say there are only 2 to the n unit vectors, roughly speaking, only exponentially in n unit vectors up to some discretization. So you can do a union bound over all of them. So if you have an event that is exponentially exponentially unlikely, it will not happen. So the maximum. So this gives you basically an algorithm, an inefficient algorithm, to distinguish between the 2 models and actually to recover the vector if lambda is larger than square root n. So above square root n, it is actually possible, but the problem is that when k is not 2, this is not a problem we know how to solve efficiently. So this does not give us immediately an efficient algorithm. One way to make to have an efficient algorithm for even k, and then these things also work for odd k, but you just have to be a little bit more careful. Is so for an even k, we can say, okay, let's think of z as an n to the k over 2 by n to the k over 2 matrix. And then if it's a random matrix, then lambda max of z will be roughly n to the k over 4. So at least if lambda is more than n to the k over 4, then you can distinguish between the planted, the spike, and the null model, because in the spike, the largest eigenvalue will be larger than will be lambda at least, so it will be larger than n to the k over 4, and in the null model it won't be. So basically that tells us that at least, so for lambda, which is roughly n to the k over 4, this is easy. And now basically we have questions of what happened in that very large range between the two, between these two. And now we come to this question where which the low degree likelihood attempts to answer, and we'll see also some other ways. How do we try to get like some sense of what's going on in these kind of intermediate regions? But that would be a good point to ask questions, and before we move to the low degree likelihood.
Why is lambda above n to the power of k over 4 easy?
So I can show one efficient algorithm. I don't know if it's the best, but and one efficient algorithm would be the following: you're given the observation y, which is an n to the k tensor. You think of it as an n to the k over 2 by n to the k over 2 matrix, and you compute its top eigenvalue. Now, if it was from the null model, this would be just a random matrix. Maybe you also symmetrize it, you do y plus y transpose. And so this would be a random matrix with normal entries. So a random m by m matrix, the largest with standard normal entries, the largest eigenvalue of that is square root m. That's kind of a standard random matrix theory result, also not that hard to prove. And then so you can compute this largest eigenvalue. Now, if it's in the spiked model, you know the largest eigenvalue will be at least lambda, because you have a unit vector that gives you lambda correlation with this thing. So if you get something much larger than n to the k over 4, say 10 times n to the k over 4, you know it must have come from the spiked model. So that gives you an algorithm. Yes?
Question about it. Is there no notion of power iteration for tensors?
There are algorithms that try to do, so there are algorithms that try to solve this type of problem. And so it's a good question. Like, I mean, I'm not, at this point, what we know is that we don't have an obvious way to try to solve this problem, and we don't have an obvious algorithm, and the obvious algorithm only works where n, lambda is n to the k over 4. Yes?
No, but so if I just look at if I want to find the largest kind of eigenvalue of tensor, is that known to be hard? In the worst case, is that known to be hard?
Yes.
Yeah, okay.
Yes, in the worst case, yes. Yes, so there is no worst case algorithm to find the largest, largest,
To solve that problem.
to solve this problem for yes so for general Z, you can embed the SAT problem essentially in this type of problem. So generally, this type of problem is, you know, one way to think about it. You're trying to maximize, say, a degree. You're trying to maximize a degree, say, 3 or higher polynomial over the unit sphere. So one easy way to kind of embed the SAT problem. So let's just do so one easy way to embed like the SAT problem, right? You can write the so if you have like the 3 SAT problem, you can write you can think of it as, you know, you want to maximize some over you know, these constraints Ci of x. Each one of those will be kind of degree 3, subject to right, xi say squared equals xi. So you can, if you wanted to walk over the unit sphere, you could, you know, you could add some, you could write something like maximize or minimize. Yeah, maximize, minimize. So we flip a sign in this case, and you could have like a penalty term like minus m times sum I of xi squared minus xi, or something like that. And so you could basically define this problem you can basically embed the SAT problem as maximizing a degree 3 polynomial over the sphere. And so generally, yes, it's NP hard in the worst case. More questions? Yes?
Is this related to the difficulty in defining a spectral decomposition for tensors? I think the general spectral decomposition theorem does not exist, right?
Yes, so I mean, this is part of it. Like all of the theory, everything that we use for matrices somehow breaks down for tensors, and it's all somehow related. So we like everything we know how to do from. So for tensors, there are different ways to define what it means to be an eigenvector, and these different ways don't give you like the same type of thing. So. Like also the decomposition into rank 1 tensors is not necessarily unique, and there are all sorts of like complications in tensors, and one of the manifestations is that we don't have an efficient algorithm to like maximize correlation with a tensor over the unit sphere. At least don't right. So so now the question is, how do we get evidence? So maybe I can, you know, break the suspense here. We believe that actually you cannot do it, that this is like an actually hard regime, that this is, you cannot do it. And there are different, various methods that give you this answer. And I'm going to talk now about this low degree likelihood, which is one approach to try to give evidence for these type of things. So now we're going to talk about the low degree likelihood. Actually, maybe I should keep this, because this is going to be quite similar. So up until now, I didn't really care about what the domain was that we were working on. For now I'll think of it as R to the. So now I have to choose, come to this point where I have to choose some letter. Let's think of it as R to the n, right? So our distributions are over, say, R to the n. And define the class. So let's fd be all the functions from R to the n to R that are, of degree at most d. Right? Just all the polynomials of degree at most d. Yes?
This is the same n. It is the same n that's there, right? You already did.
No, it's not the same n. I guess. Okay.
So n here is the dimensionality of v, right?
Right. So I shouldn't say yes. So let's not. So let's not pick. Let's say this m. Okay. So because this will be n to the k. Right. So let's say m. What? Not capital N. Is that good? Let's do capital N.
Overview.
What?
Overview. Overview. We'll discuss it.
Okay. So let's do capital N. Or, I mean, I'll most of the time try to avoid actually using the specific number. We care more about the degree than the actual number of variables. But right, so this is a linear space, right? So this is a linear subspace, the subspace of all polynomials of degree at most d. So for every f, so let's just define this is our space. So for every f from R to the real numbers, or maybe that would be a bad. For every f from R n to R, we define f, less or equal to d. This will be the orthogonal projection of f. The orthogonal projection of f with respect to this inner product into the space of degree, polynomials of degree at most d. Okay, so we have a linear subspace, we have an inner product, then we can define a projection into the subspace. So we are going to project into this subspace of polynomials. Now just notice that, so this is obviously in this subspace. And just note that, if f is of degree at most d, then obviously it can be written with at most n to the d terms. So right, all the monomials. So in some sense, we can compute it at least by a small circuit of size n to the d. And sometimes some polynomials of the degree d, sometimes we can do it in times 2 to the d. So we kind of think of maybe the most important polynomial that we often can do in time 2 to the d is the maximum eigenvalue of a matrix, which you can think of it as roughly, you can get it roughly by taking the matrix to the log nth power. So even though the naive way to evaluate this polynomial is going to be to run in times n to the log n, you can do it in time polynomial in n. But roughly speaking, because of these reasons, we are not going to distinguish so much polynomial and quasi-polynomial time, or the constant degree, or logarithmic degree. So our notion, so we basically think of if d is O tilde of 1, and by this I mean, say, polylogarithmic or O of log n, then we will think of it as efficient. So this will be our kind of a notion of, very rough notion of efficiency. So we think of if f is a degree of at most d polynomial, then we think of it as efficient. So now we want to ask, what's the so if we care only about efficient distinguishers in the sense of low degree polynomials, what's the best? If we care only about efficient distinguishers in the sense of low degree polynomials, what's the best? What's the best distinguisher we can have between these two probability distributions? So then we can do the same type of calculation, right? So so if f is a low degree polynomial, then if we look at L minus 1 f, that's the expectation of, that's all, for every f, that's the expectation of fp minus expectation of fq. But if we care about low degree polynomials, then if f, if f is at most is itself of degree at most d, then we can project the low degree likelihood, and that would project to the low degree likelihood to degree at most d. That will not matter. That will be the same. That will not change the inner product because f is already a low degree, right? Is already a low degree polynomial, right? So if f is at most d, right? If f is of degree at most d, then the difference between the bias between f of p and f of q, that's the dot product of the projection of L to the polynomials of degree at most d. Minus 1 dot product with f. Nati, you're following your bars, so.
Are you? So maybe just tell me something about the distribution of different coordinates of R and like I mean, why did yeah? I'm just trying to understand why why is it true that you only depend on low degree?
Okay, so let's go over it.
Yeah, you're assuming here something about, did you make any, in order to make this statement, do you have to make any assumption about Q? Or is this valid for any distribution of Q? In particular, the coordinates are independent or something?
No, at this point we haven't made any assumption about the independent. All we said, we have a linear subspace. So maybe the way to think about it, we have a linear subspace capital F, we have an inner product. So, and we have a projection, right? So what we say is that, and we have a projection, right? So what we say is the following. For every f in F, L minus 1 f is equal to, yes, the projection of L minus 1. 1 is obviously a low degree polynomial, so right? So the projection is with respect to the inner product. So if I project, if f is already in this subspace, I can project L, and it will be the same inner product. So the corollary of that is the following, and I maybe want to keep these things. Maybe it's not that important. So maybe I'll write the. Yes.
This notation of projecting to less than equal to b, that depends on Q though.
That's yes, because the dot product depends on Q. But I didn't assume that it's a product distribution. But the dot yes, yes. So then the corollary of that is the following. For every low degree f, say if we look at expectation of f of p minus expectation of f of q divided by the variance of f of q square root, that is bounded by the norm of the projection of the low degree projection of the likelihood ratio. So notice, if you project something, the norm becomes smaller. So this is a better bound than right. For every f period, right. So we knew that for every f period, this is bounded by this norm. Right, yes, is there a question? So for every f period, this is bounded by this norm. But for low degree f, this is bounded by a smaller norm. So so basically, so basically we say, you know, if this is at most 1, if this is at most 1 plus little of 1, then there is no weak, let's say, degree d. And so if we think of degree d distinguishers, degree at most d distinguishers, then we can look at the projection of L to to degree at most d. And now the philosophy of this low degree likelihood test is that this captures efficient algorithms. So this is the kind of low degree philosophy, that if a problem is nice, and now when we say the problem is nice, we might assume something like basically what Nati was saying, like that maybe Q needs to be a product distribution, etc. Up to now, we didn't assume anything. But the general, say, the kind of low degree philosophy is that for if a problem is nice, so for all nice problem, low degree, so maybe O tilde 1 degree is basically the same as efficient algorithm. That if there is no low degree polynomial, there isn't any efficient algorithm. Yes?
Just one question. I don't understand the statement that every function which belongs to Fd can be written with at most n to the d terms. Because if I take one-dimensional function with n equal 1,
yes.
I would need d terms, x1 plus x2 up to xd. While that is written that maximum with 1/3 with n equal 1.
Ah, okay. Maybe I said maybe it should be d times n to the d or something like that.
I think it's d
Okay.
to n. No, I don't know something, but
No, I don't think it's. How many monomials do we have? How many? Yeah, it might be like like I think of d as constant, so I don't care so much about. But I think the power is n to the d. So how many monomials do you have? How many monomials can you have? You basically can choose each variable, like each monomial. You can choose. Yeah, so I think it's maybe it's n plus d to the d or something like that.
I think this is the sum on j goes from 1 up to d of n to the j or something.
Yes, so it's basically n to the d. It's O of n to the d. Yes. Yeah, if you wanted to put d in front of it, that's fine. Yeah, yes. Like d is O of 1, right? So, yes. Yes. Yes, no. Yeah, you're right. Yeah, I mean, usually, yeah, sometimes sloppy with these constants, but it's good to be precise. Other questions?
So this is the corollary of.
What?
So you wrote corollary, right?
Corollary. I mean, corollary of this maybe of this fact that basically, if you project to low degree, then the dot product, this dot product, you might as well project, right? So last time we showed that this is true for every f with respect to the norm of L minus 1, and basically if you project, if f belongs to the subspace, then you can project the likelihood to degree less than d.
Okay, so this is just a way to restrict ourselves to a polynomial thing where everything is a little more bounded than in the.
Yes, so this basically, so now the low degree philosophy is that that this quantity captures the efficient, so this quantity, which is smaller than the norm of the general likelihood, captures the power of efficient algorithms. So if you wanted to, so now we can try to say compute this quantity, and maybe we'll get a different answer, and we believe that this answer so for nice problems. So now there is a formal, there are some formal conjectures. Maybe I'll say a little bit later some examples of the formal conjectures. But there is, generally what the people mean by nice problems typically requires several things. So typically what people assume as a nice problem is that the null distribution is a product distribution, and the planted distribution satisfies some nice symmetries, like so in a planted tensor, etc. There are like some natural symmetries that it satisfies, and that it is somewhat noise tolerant, the planted distribution. So there are some. We'll talk a little bit about noise operators later. So it's somewhat noise tolerant, and there are some results showing that these assumptions are actually necessary to make formal conjectures. But for now, let's just say this is the general philosophy that if your problem is nice, then the low degree likelihood should capture it. And how much time do I have? 45 minutes, good. So I'm going to, yes, so first I'm going to show, I'm going to calculate this low degree likelihood for the planted tensor problem. And then we're going to go into talking about low degree polynomials in general and proving some properties of low degree polynomials that are in general going to be useful for us. So let's do the calculation for tensor. Okay, so or at least I'll do a kind of a cartoon of the calculation for the tensor. Okay, so we are back to the same example, this spike tensor problem. So we said that we have y, which is v tensor k lambda v tensor k plus z, and we recall that L squared was this expectation over uv LU LV, which was expectation over UV e to the lambda squared UV to the k. Okay? So now if we now look at the projection to degree at most d, that by the same reasoning will be LU, the projection of LU, LV to degree at most d. Now, it turns out, and this is some calculation that I'll skip, it's not actually trivial, and it has to, and you need to use some, but at least it's kind of believable, that basically what happens is you do the Taylor approximation to E, and you truncate it at D. And so basically this will be expectation UV, sum little d from 0 to capital D, lambda squared UV k to the power little d divided by d factorial. Okay, so if you wanted to, so if you want to so this is not always true, and it uses the probability particular thing that the null for us was a Gaussian distribution. So in the Gaussian you have a very so it turns out that the projection, the orthogonal projection with respect to the to this distribution really just gives you the Taylor approximation. Okay, so this would be a statement that would have required a proof, but at least it's kind of believable, right? So now just remember that L became unbounded. So generally this is larger than this, might be even much larger, right? And just remember that L itself became unbounded once lambda was larger than square root n. Now our question is, if we think of d as a constant or logarithmic or something like that, how big lambda needs to be before the truncation, the projection of the low degree projection of L also becomes unbounded. Okay, so now the dominant, right, so of course we can switch the order of summation and expectation, and also the dominant term will be the last one. So we basically are looking at expectation over uv of lambda squared uv k to the power d divided by d factorial. Right, and now this is actually quite nice, right? So uv dot product uv behaves like a normal with variance 1 over n. And if k is if k is a constant, a finite power, then up to some factors that depend on k, this is basically the expectation of uv to the k. That is going to be basically so think of d, right? So if we think of d as some constant, and so if we think of d as a constant and k as constant, then this would be roughly, so this would be roughly lambda to the 2d and square root n, 1 over square root n, square root n to the minus kd. Right? So dot product of uv, the expected dot product of a power of a Gaussian, of a standard Gaussian will be of a Gaussian with standard deviation 1 over square root n will be 1 over square root n to that power times some factors that depend times some factors that are constant, if you think of these powers for constant, right? So up to some constant. So basically, up to some constant that depend on k and d, we get lambda to the 2d square root n minus kd. So now we can see that this goes to infinity. So basically, this goes to infinity if so this will be infinite if lambda squared is larger than n to the k over 2, or n will be bounded if lambda squared is less than n to the k over 2. So we get that the threshold is lambda which is n to the k over 4. So basically, we get this answer. So we see that beyond, so we see that what happens here is that here low degree is infinite, and here is bounded. So just again to emphasize, so in all of this regime, the likelihood is unbounded. The likelihood which is not low degree, but only in this regime the low degree likelihood is bounded. Right? So the low degree likelihood actually predicts that the efficient threshold would be at n to the k over 4. Yes?
If we control more precisely all the logs and constants and stuff like that, could we have access also to the constants in front of this phase diagram, or it's only at the level of the powers of n?
So okay, so you could try to do. I mean, what you really need to do if you want to control more things is not to think of efficient versus inefficient, but rather. So now the question. Okay, so let me erase. You can erase the philosophy. So what people have done is so you can think of it the following. You can do this map, like the degree that it is required to refute, to certify, and then say lambda, which is square root n, and lambda, which is n to the k over 4. So generally, this degree, say, going from n to, so n would be kind of like exponential time, and 1 or constant would be, so people have given trade-offs that, it probably looks something like, yeah, I'm not sure exactly the shape. Some people have done these things where they basically say, okay, if lambda is some n to the alpha, what is exactly going to be the degree, and as alpha ranges from square root n, etc. I don't know if these predictions have been down to the constant, and I think at that point you also have to start to be a little bit more concerned with the differences between weak and strong distinguishers, and so you might have to be a little bit more precise also in what is the task, what is the running time, etc. But the one, so I'm not sure if people have gotten to that level, but the one thing that people have done is map out like the dependence between the degree, and people do believe that this will capture like the sub-exponential also. So when you're here, it's not that you need the exponential time, you need something like sub-exponential, and people believe that they know the sub-exponential behavior. Yes?
So the way you write a proof, it looks a bit, completely unconstructed. You are basically saying there is a function, there is a low polynomial that can make the distinction.
Yes.
But you are not telling us which one.
Right, although I did tell you before, because the spectral, yes, so I did tell you before because the spectral algorithm is actually a low degree polynomial. So if you take the maximum eigenvalue, yes, so it's like the trace of, you take this tensor, you think of it as a matrix, you trace it out, that will be the particular low degree polynomial in this case. But yeah, in general, this part is the kind of the low bound. So this part is the low bound.
So,
yes.
So here we recover that if lambda, we recover that the easy phase transition part, right? When lambda is again larger than n to the power of k
No.
forward. then
No, we say that we show that if lambda is smaller than n to the power of k over 4, then this is bounded, right? So if lambda is smaller than n to the k over 4, then this will be bounded. So this shows that there is no low degree distinguisher when lambda is, so this gives evidence that this is an actual phase transition, that in this place, if you think that if you buy the low degree philosophy, then this is actually hard. Then this phase is hard because no low degree algorithm can distinguish in this phase. So if you buy the low degree philosophy, then this part is hard.
this is the consequence of the first theorem that we had.
What?
Is this the consequence of the first theorem we had?
Yes, this corollary that was there, that low degree. So the low degree philosophy is basically one, if this, say, specifically if it's significantly smaller than n to the k over 4, say little o of n to the k over 4, where by little o I mean smaller than any factors depending on d and k, then this will actually be 1 plus little o of 1. So there is no even weak distinguisher that is low degree, and then the low degree philosophy says the problem should be actually hard. Yes?
Can you comment on this operation of flattening the tensor to a matrix?
Yes.
What kind of properties would one expect to be lost there and what preserved?
Okay, so the question is what you do with the matrix, right? Like flattening by itself, like, or vectorizing doesn't lose any information. The question is what you do with the matrix. And generally, like when you flattened and you looked at the maximum eigenvector, you basically, instead of maximizing over, you're maximizing over much larger space. So instead of maximizing over unit vectors in n dimensions, you're maximizing over unit vectors in n to the k over 2 dimensions, which is a much larger space. So, but it's one that is easier, but you've made it into a convex problem. So basically what you've done is you've taken, this is basically a convex relaxation, right? So you've taken a non-convex problem, which is maximize a function over some non-convex set, the set of all, one way to think about it is, right, the set of all vectors that in n to the k, say, in n to the k dimensions that are tensors that are like tensors of rank n, and you made it into a convex problem, into an eigenvalue problem. So by looking at a much larger convex set that contains it. Yes.
If we want to be more precise, like we should also be able to exclude high degree polynomials that have only a few terms, right? Because there are high degree polynomials that can be evaluated efficiently. Right.
So I guess what we believe in this low degree philosophy is that if you're willing to ignore like the difference between constant and log and poly and quasi-poly, then you should then this will be fine. Then the higher degree polynomials will be inefficient. And let me in a second we'll say why we believe that a higher degree polynomials. So in general there are functions that you can compute efficiently that are higher degree polynomials, but we somehow believe they are not going to be relevant for nice problems, and we'll give some intuitions in soon, like why we believe this. Remind me when is the end? What, in 10:15? Okay, so I have like 25 minutes? Good. So basically, what I want to do now is I want to talk about so I want to talk about general intuitions about low degree polynomials that are just true in general, general facts about low degree polynomials that are going to be useful for us later on. Okay, so but before I can erase the board, and then any questions? Okay, so I'm going to erase the board. Feel free to take a breath and stretch if you want to. Okay, so now I want to talk about general intuitions about low degree polynomials that are, or general facts about low degree polynomials that are good to know. So the two things that you kind of want to know about low degree polynomials is the following. So this is, I'll write it as intuition. These are formal theorems, but there are different ways to formalize these things as theorems, so that's why I write it as intuitions. And so intuition one is that low degree polynomials are insensitive to low probability events. And intuition two that adding noise makes functions become low degree. So generally, they're also insensitive to noise. So low degree polynomials are robust to noise. And basically, they're in some sense the only things that are robust to noise. In the sense that if you add noise to, if you kind of noise up functions, then they become close to low degree. And there are different ways to phrase these things. And so I'm going to start by talking about intuition number one and one phrasing of it. So what does it mean that it's kind of insensitive to low probability events? So let's think about a function. What does it mean to be sensitive to a low probability event? So suppose you have some function f, and it looks like this. Right. There is. So what does it mean? What does it mean? Like it means that there is an event that has a probability mu, which is goes to 0, like a very small probability mu, that contributes. So to say this is an event A with probability mu that contributes, say, at least an epsilon fraction of F's norm. Right. So that would be like a function that is sensitive to. That is sensitive to a low probability event. So basically, a function like that would satisfy that, say we normalize expectation of f squared is 1, expectation of if x in A. So expectation of, say, f squared times 1a is at least epsilon. And the probability of A is mu that goes to 0, where epsilon, you think of it as a constant. Okay? So in this case, expectation over A, if you condition on A, of f squared is, is at least epsilon over mu. So, right? Nothing special here. Okay? Yes, no, no. So yes, or maybe you're just trying to figure out if you have a bed to sleep in tonight. So yes, you might. Yes.
Only the field, that just need to know.
Yes, or if I have a bed to sleep, yes, yes. So yeah, we should. Yeah, I mean, apparently it's not only San Francisco, also Les Houches has a homeless problem. So expectation of f to the 4 will be at least, right? At least a contribution from A. So at least mu times, by Cauchy-Schwarz, it will be at least mu times epsilon over mu squared, which is epsilon squared over mu. And the main point here with this calculation is that this actually, right, goes to infinity. If mu goes to 0 and epsilon is a constant, this goes to infinity. So so one way to think about it in such a function, if it's sensitive to low probability events, then the 4 norm of f, if we think of this expectation norm, the 4 norm of f is much larger than its 2 norm. And like when we define the norms with expectation, so this is basically so this is basically an example of a function that is not that is sensitive, and low degree polynomials on nice probability distributions, they're generally not sensitive, so they will not not have this property. So for now, let's prove some stuff. And I'm going to take the most simple setting. So I'm going to consider, for this part of the talk, which is probably like until the end of the talk, I'm going to consider only functions that map plus minus 1 n to the r. And we're going to consider the uniform distribution over plus minus 1 to the n. So here is one very nice lemma. This is known as sometimes as Bonami's lemma, sometimes as 2 for hypercontractivity. Or it's but exactly why this is hyperconductivity, maybe we'll see in a second. This is not, but the lemma is the following: if f is a function from plus minus 1 to the r, and the degree of f is at most d, then the expectation of f of x to the 4 is at most 9 to the d times the expectation of f of x squared. So, sorry, f of squared, right, so to make things. Right, so this basically says that if, say, you think of d as constant, then the low degree polynomials are not sensitive to low probability events. It cannot be the case that their norm gets, like a lot of the mass of the norm comes from a very low probability event.
There are no restrictions on the law of x here.
No, it's uniform. It's a uniform distribution. This is with respect to x according to the uniform distribution. This is with respect to product distribution. Yes. Yes. Otherwise, it will not be true. So let's prove this thing, because it's not nice to never prove anything in a lecture. Okay. Even though the proof is calculations a little bit, but so you prove it by induction on n. Okay. So yeah, base case we don't really care. So let's write. So we can write f as xn times, say, f1 plus f2. So basically, I take all of the monomials that involve xn in them, and so we write this part xn times f1. This is the sum of all the monomials that involve xn, but take the xn out, and f2 is all the monomials that don't involve xn. So in particular, the degree here is at most d minus 1. Okay, and now we just going to do these calculations. So let's start with expectation. Let's start with expectation of f squared. So expectation of f squared. We can do it expectation of xn squared f1 squared plus 2 xn f1 f2 plus f2 squared. And now some facts that are useful, and we're going to use right. So some facts that are useful. They are uniform distribution over plus minus 1. What is xn squared? 1, right? So it's always 1, so we can erase that. And what is expectation of xn? 0. And f1, f2, they depend only on the first n minus 1 variables, right? And this is and this is a product distribution. So expectation of xn is 0, and it's independent of f1, f2. So that means this part also dies. So basically, expectation of f squared is expectation of f1 squared plus expectation of f2 squared.
Sorry.
Yes.
Do you have some xn in f1? Maybe.
No, you can. You don't have xn in f1. Is another thing. Very good. You don't have powers larger than 1 in the monomials because x1 xn squared is 1. Very good. Okay. So now let's now let's do the calculation for f4. So now we do this, right, so we do this binomial thing, right, so we get xn to the 4 f1 to the 4 plus 4 xn 3 f1 3 f2 plus 6 xn squared f2 squared plus 4 xn f1 f2 cubed plus f2 to the 4, right? So now we can do the same kind of arguments. So even powers of xn, they just are 1, so we can erase them. Odd powers are 0, and they're independent from odd powers are 0, and they are independent from the rest. So these terms just die out. So we get right f1 to the 4 plus 6 f1 squared f2 squared plus f2 to the 4. Now we can use our induction hypothesis. Right. So we can apply inductions on f1 and f2. So we get that expectation of f to the 4 is smaller by the induction hypothesis, the 9 d minus 1 expectation of f1 squared plus we're going to do some Cauchy-Schwarz, right? So we're going to do a Cauchy-Schwarz and bound this by the for expectation of this square root. So maybe I'll write this nicer. 6 square root expectation of f1 to the 4 expectation of f2 to the 4. Right, so here, so we can apply the induction hypothesis. So here we get 6 the square root of 9 to the d, 9 to the d minus 1 expectation of f1 squared, all that squared, and 9 to the d expectation of f2 squared, all that squared, plus 9 to the d expectation of f2 squared. Okay? So now let's just kind of write a square. We can make this square root go away by making the 9s into 3s and getting these squares out. So we can write this. So it's 6 times 3 to the d minus 1 times 3 to the d. We like this form of 9 to the d, so we can write it as 9 to the d times 2. Okay, people are good with that. Write 6 times 3 to the 2d minus 1. Divide by 3, you get 2, and then you have 9 to the d. So we'll write it as 9 to the d times 2. So now just let's look at what we have here. Let's make it even 9 to the d here also. So what do we have here? We have 9 to the d times expectation of f1 squared plus 2 times expectation of f1 squared times expectation of f2 squared plus expectation of f2 squared. So this is exactly the expectation of f1 squared plus expectation of f2 squared, all of that squared. Right? This is 9 to the d, expectation of f1 squared plus expectation of f2 squared, all of that squared. So which is exactly what we wanted to prove.
So do we do induction on n or on d?
Both. Or maybe formally the induction is on n, but the inductive statement is that it's true for all degrees up to d. So maybe the inductive statement is of n, but the induction is on n, but the statement is for all d. So the inductive,
Separate.
or
On d we can prove this by induction.
yes, for all d we prove it by induction. So the base hypothesis, you have to prove that for if you have a one variable function, then this is true for all d, and then basically based on that you prove this for yes. So the induction, the inductive hypothesis is that this bound is true for all d. Okay? Does that make sense? So right, so the inductive hypothesis is that for the if you depend on at most n minus 1 variables, then this statement is true as stated for all degrees d. So in particular we plug this in for d and for d minus 1 for the f1 and f2. Okay. So this demonstrates that this demonstrates that these low degree polynomials are not sensitive to small events. Yes.
But you're really relying here on the fact that it's over plus minus 1.
Yeah, I mean there are like similar type of things for Gaussians. Like similar results are also true for Gaussians. For random Gaussians, you're assuming that this is a product distributions but similar.
Related to, because your notion before is much more general, right? Of degree with respect to you had some general distribution.
Right, but generally, I think you left when I yes, I mean generally like for the places where it would make sense is for when Q is nice, and typically by nice I will think of it as a product distribution. And either Gaussians or plus minus 1 or something else that's kind of nice. And then you typically have this type of results. And by the way, these things also generalizes So the general, more general statement that is also known is that, and can be proven kind of similarly, I guess. I mean, maybe that you'll generally have that the Q norm of F is at most square root Q minus 1 to the D times the 2 norm of F. So that's the general, more general norm, more general form. And now let's talk a little bit about the second intuition. Wow, a little is very, okay. So let me maybe just say it.
Just to understand.
Yes.
So this is a statement about how much local can the function f be on the data space.
Yes, yes. And one way to think about it is that this basically, here is kind of an intuition that you could think. If f is a degree d polynomial, it can only be close to, say, an indicator of a set if the set has measure at least, say, inverse exponential d, at least something like constant to the minus d. It cannot be smaller than that. So basically, low degree polynomials can kind of correspond to events that happen with probability 2 to the minus d or something like that, but not less than that. So they cannot depend on two small events. And the second intuition, which I don't have a lot, so you can think of the various noise operators. So here are kind of two that are most maybe important. So you can think of, say, t rho applied to a function f would be the function, would be the following. So t rho of f would be this, let's call it f tilde, such that f tilde of x is expectation over y, which is rho correlated with x, of f of x. So this is basically like you take, you noise up a function. So you take a point x, and you take some random y around, like a small ball around it, and you take the average around this ball. So what does mean y correlated with x? There are two natural ways to think about it. One is that, say, in the plus minus 1 setting, the thing that makes sense is that yi equals xi with probability. So if, say, rho is 1 minus epsilon, then I think yi equals xi with probability 1 minus, I never remember if it's 2 epsilon or maybe with 1 epsilon over 2 and equals minus xi with probability epsilon over 2. The basic idea would be that independent for each y. So expectation of x, yi xi will be rho. So yi will have the same marginal, the same, say, will also be Bernoulli, but will be rho correlated with xi, and then you do this independent for each coordinate. And in Gaussians, you will set yi to be something like rho xi plus square root 1 minus rho squared standard Gaussian z. So you basically, you look at this, at some kind of a noise operator, and then what you can show is that basically this noise operator tends to harm high degree terms much more than low degree terms. So this is some calculation which I'll not get into because we are already behind time. But one corollary of these things which I want to state, this is actually when people say hypercontractivity, this is what they really mean by hypercontractivity. So this is the hypercontractivity theorem. That for every f mapping, this one doesn't have to be low degree. And for every q, say, that is between 2 and infinity, t 1 over square root q minus 1. If you apply this noise operator to f then the norm Q of this is at most the 2 norm of F. So this is some calculations which I'm not gonna. So basically, the notion of hypercontractivity is that this operator shrinks F even when you go from Q to a smaller norm, to small norm smaller than 2. And so this is this noise operator, and basically one way to say is that this function behaves like a low-degree polynomial. After you apply the noise to it, it behaves like a low-degree polynomial. This has been found tons and tons of uses in many fields. And I'm going to end now, but if you want to know more about it, there's a really wonderful book by Ryan O'Donnell called Analysis of Boolean Functions, and it's also available freely online. So, please, go ahead and look it up. This is a whole beautiful theory of, which I didn't get into, but maybe I'll mention more if I need it. But I think with this I'll finish. But generally, the philosophy is that low degrees are insensitive, and one part of this philosophy that's useful for us is that the low degree likelihood, unlike the usual likelihood, the low degree likelihood tends to not be sensitive with nice distributions so the contribution to the norm doesn't come typically from very low probability events. So typically, I don't know if there are formal statements always, but typically we get like an if and only if. If it's small, then there is an actual, then there is no algorithm, and if it's large, there is an algorithm. So, yes?
So in the context of phase transition, we can say that like if the indicator function is low degree, then there'll be a phase transition because it will always be, it will always appear either with high probability or not appear with high probability.
Yes, something like that. So yeah, I mean, we could try to make things more formal later, maybe after, like we have to release everyone's, get them ready for Chaim's talk. But basically, but these two facts are very useful about low degree polynomials, and there are all sorts of things. So basically, there is all sorts of theory around it that will, maybe some of it we'll see. And more questions? Lenka, do you have a question? Or?
Yeah, I'm not sure I understood the second intuition, like in which sense the noise makes the functions low degree.
Okay, so first of all, it makes it satisfy the similar type of property. And the second thing, and this is where okay, so maybe I'll just say this. This property, very easy to show that if you take a monomial, like say, if you take a monomial x product I in S xi, then if you apply T rho to it, then you basically get rho, like the expectation. T rho applied to this will basically be like rho to the S times IS. The expectation of, say, T rho applied to it will be T rho, sorry, not expectation. T rho will be the function rho to the S. Yes. So basically, what you'll get, yes. What you'll get is that, right, T rho gives you, T rho to the monomial is like the expectation, is the expectation of the product of I in S, yi, but yi are all independent and they're all rho correlated with X, so that will be rho to the S, the original monomial. So basically what you see is that T rho shrinks each monomial, but it shrinks it more if it's higher degree, and it's exponentially more. So if you were to write, so I'm using you as an excuse to say just one more thing. So if you were to write, say every function f, you can write f of x as a sum of coefficient for s, x to the power s, right? Like this is just write it as a polynomial. And when we are over plus minus 1, then the polynomial, all the monomials, it's really sets and not multisets because there is no need to have power larger than 2 because xi squared is 1. And if you apply, if you do t rho of f, then of x, that will be sum rho to the size of s, cs, xs. So you see, it's basically shrinks the high degree terms of f. And so basically, the noise operator shrinks the high degree terms, and that can be, in that sense, it makes it more like a low degree polynomial. Yeah, and I should say that typically the way people write this, they write cs, they use this notation, f hat s, because that's the Fourier coefficient of f with respect to this, if you think of the group plus minus 1 to the n. Okay?
Okay, if no other urgent questions, let's take the questions offline. And
Yes.
you pause.
Thank you.
Thank you.
Thank you.